recording here. Okay, gotta love it. All right, guys. Looks like I'm on the air. All right, guys. Video number 24. And what I want to do, we're going to get a few couple of topics today. First thing. We're going to look at techniques to make inferences about our intercept. Next thing we want to do is we want to make inferences for predicted values. And we're going to do this in two cases. We'll do this in case number one where the parameters are known. I'm sorry. We'll do parameters unknown first. And second, we'll do where the parameters are known. And the sampling distributions for those vary a little bit. And, well, I mean, they're just two completely different situations. And although they're very similar, but they do have different parameters. So let's start this out. The data that I want to use, we used this in a previous video, and it kind of makes sense to all of us. We're all in education, and it's a simple data set. Easy to type in. 832, and then we have some GPAs. So we had 2.4, 2.2, 2.8, 2.9, and 3.5. So here's the data that we're going to use. And I've gone ahead and thought this through just a little bit. Some of the standard errors that we're going to create, there's a couple things that we're going to need. And one of the first things that we're going to need is our value for the for sigma squared, which remember is the mean square error. We're going to need the mean for x squared, and then we're going to need the sum of our x sub i's minus x bar squared, so the deviations of the x values from the mean quantity squared. Now we may need some other stuff too, but we can make it happen from let's see, I'm kind of second guessing myself. Now I think this is it. I think if we get these three values, we're going to be in pretty good shape. So guys, let's run over to R, and you'll notice that to save time, I've already gone ahead and put the data in. And to get sigma squared, the estimate of sigma squared, what we need to do is find the standard deviation of the error. So probably the best way to do that is like we've done it before. So we have linear model and of course GPA, ACT. And if we look at our model, all we'll do is just get the parameter estimates. But if we do summary of our model, we get some other things. Now, a couple of things I want to point out to you is residual standard error here of 2.2477. Well, if we square that, we get an estimate of our sigma squared, which is the very first thing we need. So I'm going to write this down. 2.24. And once we get back to the blackboard, we'll have that information there. Something else I want to write down. This lecture starts out examining this this line. So I'm going to write that down too, and I encourage you to do the same thing. So our B0, or beta hat 0, is 0.648. Notice the standard error of our B0 is 0.586. Notice our test statistic is the t-value, which is 1.107. And notice that we have a p-value, and I'm writing this down, 0.3492. So our slope, our intercept is not statistically significant. We can go ahead now. The next thing I told you we needed was the mean of the x's squared. So, I mean, that would be easy to do, just mean ACT. And quantity squared. And we get 625. And then we want to take each observation, subtract the mean, or each x, I should say. Subtract the mean, square it up, and then sum. So what we can do is we can take our ACT minus the mean of the ACT, and if we square that up, and then actually I need to take the sum of that. And I'm going to copy and paste that. I should have set that up when I set it up initially, but alright, so let's get rid of all this. Alright, so when we sum this up, we end up getting 116. And guys, you can easily make these calculations on your calculator. But I don't have the TI-8483 emulator installed on this computer, so I just make the calculations using R. Alright guys, so let's go back to the blackboard, actually the chalkboard, and you can see I've jotted some things down. So 0.2477 quantity squared gives us 0.0614. So we got 625.0614, 116. And then these values down here, I want those here just so we can refer back to them, because we're essentially what I'm going to be doing here is showing you how we conduct inference, which, anytime we conduct inference, we're talking about the test statistic and the p-value. Hopefully we understand that by now. All right, guys. I have no idea why I did that. All right. So what we want to do is I have to just go ahead and state this just for the record. Rarely do we care about our inference on beta 0, but there could be some cases where we could. So guys, first of all, let's talk about our our point estimate. So we can find B0, of course, by taking y bar minus the product of our point estimate of beta 1 times the sample mean. Now, the same conceptual framework for the inference on beta 1 applies for beta 0. This is real important in terms of getting through this, as swiftly as possible without, leaving stuff out. So, so guys, one of the first things we want to do, as we'll always want to do, and this is a point that I've tried to make since back at video number 2, is for us to be able to calculate a p-value, we have to understand the characteristics of the underlying sampling distribution. We can have a z distribution, we can have a t distribution, we've looked at f distribution, we've looked at the chi-square distribution. So depending on what we're doing, the type of test that we're conducting, we have an underlying sampling distribution. Well, I've kind of let the cat out of the bag here, because when we ran the analysis on R, we saw that our test statistic was a t-value. So we understand that our sampling distribution is the t distribution, and so we know that our b0s follow the t distribution. Degrees of freedom n minus 2. And the mean, much as you expect, expected value of b0 equals b0. So our beta 0 is estimated by b0, and so systematically over a long sequence of trials, it doesn't tend to overestimate or underestimate. It's always a good thing. And it turns out that our variance, I hope I allow enough space here to write, is sigma squared 1 over n plus x bar squared over the sum of x sub I minus x bar quantity squared. I hope you can read that. So let's think about this. So this will be our estimate of the variance. So we'll use s squared. All right. Now, just as beta 1, our test statistic, is equal to beta 0 minus our claim beta 0 over the standard error for beta 0s. And again, this follows a t-distribution, degrees of freedom n minus 2. Our confidence interval, just as before, can be calculated by taking our parameter estimate, adding and subtracting our margin of error, which gives us our t-critical. Times our standard error. Okay, so kind of a note of caution here. We have to use extreme caution when interpreting results for beta 0. And about the best way to look at this is the results are completely meaningless. Well, not completely meaningless, but mostly meaningless, unless 0 is in our problem domain. Now, keeping it as simple as possible, if we want to examine the relationship between people's height and their weight, well, x equals 0, which would be someone's height being equal to 0 inches, centimeters, whatever it may be, that's completely meaningless. So 0 would not be in our problem domain because a person can't have a height of 0. However, if we were looking at x being say the number of siblings, in a house, y equal, well, let's just call it disposable income. Well, you can imagine clearly, and you probably know, houses that have no siblings. I'm sorry, I don't mean siblings, goodness gracious. No number of children, or dependents, if you will. So we all know houses that have no children. So 0 would be in our problem domain. So in that situation, the inference on B0 would actually take on some meaningful results. So guys, it'd be really easy to pop this out. Okay, so first thing I'd want to do is I want to make calculation of the estimate of our variance for the sampling distribution of B0. And guys, remember, this was S squared times 1 over n plus x bar squared over the sum of this. Well, let me go back and get some information. S squared was 0.2477 squared. We have n plus equal 5. Our mean was 25, so that squared is 625. I can't remember. I think I do. Yeah, 116. Okay, so we have 116. So guys, what we get here, put that in our calculator real quickly. And we get 0.3428. We're most interested here in standard deviation, because this is the value that, or I'm sorry, the standard error. So we need to take the square root of 0.3428. So raise that to the 0.5 power, we get 0.5855. So all the calculations we're going to do in terms of calculating our p-value and so on and so forth is going to be used. Our test statistic and our confidence interval is going to be use 0.5855. So guys, very quickly, we know our test statistic is our B0 minus B0 over the standard error for B0. And let's just assume here that we're testing beta 0 not equal to 0 versus beta 0. Well, testing beta 0 equal 0 versus beta 0 not equal to 0. I forget what my estimate was. Go back to R and get that. So my estimate for the intercept was 0.648. And divide out by our standard error, 0.5885. So we get a test statistic of 1.101, which is precisely what we expected to get. All right, now you might say, well, we got this gives us 1.107. You know, we have to appreciate that we have rounding error. I've rounded some things to 3 places, 4 places, because I don't want to sit there and write out decimals. So let's go ahead and calculate the p-value. So in the t-distribution, our p-value is going to be the area under the curve to the right. And I'm going to use the 1.107. And to the left of negative 1.107. So let me get that to where you can see it. Okay, so it's this area plus this area. So guys, we can use our calculator, or we can use our use R. I'm going to use R. It's just quick. So I need P of t, and we have negative 1.107 degrees of freedom equal to 3. And we need to multiply that by 2. Okay. Oh, so PT, negative 1.107 degrees of freedom equal 3. And multiply that by 2. So we get 0.349. So again, appreciating rounding error, we can see that we get the same p-value. So in this case, our tested, B0 is not statistically significant. So just an aside, we're expecting our 95% confidence interval. To contain 0. We didn't reject that beta 0 is equal to 0. And so we're going to expect to get this. So guys, again, our point estimate here is 0.648. We need our t critical, so let's go find it. So use R. So we have QT, and we have a 95% confidence interval, so we need the left tail to be 0.025. Degrees of freedom equal to 3. So we get negative 3.182. Times our standard error, which is 0.5885. I think. Yeah. All right, just very quickly, so 0.648 minus 3.182 times 0.5885. Do the plus of that. And we get a confidence interval which ranges from negative 1.22 to 2.52. So just as we expected, our interval contains 0 because we don't have statistical significance. All right, I'm not going to beat a dead horse here. There's really not a lot more to give you there. So now what I want to do, it's okay. Yeah. Who you calling? Okay. So next thing I want to do is look at the interval estimation for a predicted value. And the notation we use here is the expected value of some y sub h. So when we see that, we're just thinking in terms of we're predicting a value. We know values are going to vary. There's going to be a sampling distribution. So just a motivation here. Let's say, for example, that we wanted to focus on, back with this whole ACT GPA relationship. And what we want to do is we want to focus solely on an ACT of 32. Now, we're going to let x sub h denote the level of x that we wish to examine. And the result of this, our x sub h has its own sampling distribution. It's to be expected, right? So in our situation, we're going to examine x sub h as an ACT of 32. So guys, if we examine this, we're holding x constant. And we examine the variability and central tendency of the y's. So for example, it wouldn't be out of the realm of believability if we had a person of an ACT with 32 that had a 1.9 GPA. Next person with a 32 may have a 3.8 GPA. Another person with a 32 may have a 3.2 GPA, and obviously this could go on and on and on and on and on. So we figured this one, this is what I would call my y sub 1, this is my y sub 2, this is my y sub 3. We wouldn't expect these things to be the same, so we expect them to vary. So this brings up the sampling variability examination via the sampling distribution. Well, things we know is the predicted values will be normal. The expected value of our predicted value will be the expected value of our y sub h. That's just saying that, you know, over a long sequence of trials, we don't expect any overestimation, underestimation. And the variance of our predicted values looks something like before, except for one term. Okay, we need to make that clear. Okay. So guys, in estimating this, we would look at, of course, the variance of the predicted values would be equal to s squared, mean square error, over the same stuff. All right. So guys, really not much difference than what we did before. Now, in terms of showing this part right here, that this is actually the variance of the sampling distribution, this is actually going to be a homework problem, so you're going to see that on your own with a little bit of guidance from me. But we can show that you know, the expected value of our predicted value is just going to be the expected value, as you would expect, of this, which is the expected value of this, which is beta 0 plus beta 1 x sub h, which of course is the expected value of y sub h. All right, or the mean of the y's. Now, I don't think, well, I'll tell you what, let's go ahead. It shouldn't be surprising that the test statistic is our predicted value minus the expected value over the standard error for our y sub h's. And our let me just go ahead and write this. I want to confidence interval, of course, is going to be the predicted value times the standard error. All right, guys. Let's just come up with a kind of a new model, and let's say that that we see that we could predict our GPA by taking 0.648. No, this is times our ACT. Actually, I believe I wrote that down. I think I wrote it down 0.648, 0.04, 0845. Yeah, okay, so this is the one we did. I wrote this down earlier, and it seemed reasonable to use it. So guys, for again, focusing on an ACT of 32, we know that the estimated GPA for a 32 is equal to 3.35. So guys, this serves as our point estimate of the predicted value. As this value will certainly vary. Well, let's just say it'll certainly vary. So we can now explain the variation by looking at the sampling error. Which is equal to the mean square error. I'll tell you what, let me be consistent here. 1/5 plus what we'd have here, we'd have our 32 minus the mean of our ACTs. And I forget this, I think it was 116 that we'd have there. So the calculations would be easy. I'm going to leave this and I'm just going to say easy calculations because it's very, very, very similar to what we just did for B0. So we'd have to find the mean. I think the mean was what, 25. So, and of course we know that the standard deviation, standard error of the residuals squared. I forget what that was, but we could easily look back and get it. But we got bigger and better things on the agenda, so let's keep plugging along. So we also, again, to do our confidence interval, our predicted value, I forget what was that, 3.35. So we could take 3.35 and add and subtract margin of error, which we know how to do. Okay, now let's change things up a little bit. So let's do an example here. And let's say we want to construct a 99% confidence interval for an ACT equal to 35. So guys, let's think of all the things we need. First thing we need is we need S squared. Easy to get. Next thing we need is we need the mean of the x's, mean of the ACTs. The next thing we need is we need the sum of our x of i's minus x bar squared. And then obviously, guys, we need the predicted value for this when ACT is equal to 35. So I'm going to fill some of these out. I'm just going to use the calculator because it's handy and dandy. So guys, remember S squared. It's kind of hard to remember all this stuff. So we have 0.2477. And I'm always fearful that I'm going to make a mistake and do something in my head and assume something's a particular value, and then get down to the very end and we have a wrong answer, and I drive myself absolutely batty trying to figure out what the heck I did wrong. So I'm doing some calculations in the background here. So S squared is 0.0614. And it looks like, and let me just check to make sure that the mean is 25. So the mean is 25. The predicted value for 35, let's see, let me go ahead and get our sum x. That's 116. And our predicted value for 35, let me get back to the, so what I'm doing is filling in these values. So putting 35 into our model, so we get 0.648 plus 0.0845 times 35. So we get 3.61. All right. Now, changing this up because, you know, things are going to vary here. So what we need to do now is our predicted value is 3.61. And we need to find our T critical, which is going to vary a little bit, times our standard error for the predicted values at the level. So of ACT of 35. So let's do that. So we have 0.0614 times 0.2. And here we're going to get 32 minus 25, so that'll give us 49 divided by 116. And if I did everything correctly, our standard error is 0.03822. Now we got to find our T critical. Guys, change things up on you just a little bit here. So what I need to do is I need to find Q of T, and we have 99%, so I need 0.005 degrees of freedom equal to 3. So I get negative 5.84. As obviously 99% confidence interval, our margin of error is going to be larger because we have a higher probability of creating an interval. Well, our interval has a higher probability. The probability of our interval containing the predicted value increases, so we have to have more margin of error. So guys, at the end of the day, we take 3.61 minus 5.84 times our standard error, 0.03822. And of course we do the plus. So guys, the 95% confidence interval that I get here is 3.39 to 3.83, assuming I didn't make any typos. I know I did the correct procedure, but going from R to calculator to this chalkboard thing, it's sometimes easy to do. So anyway, not making excuses, just keeping it real. So if there's a typo, I'm sure you caught me. Okay, so what this says is that if an admissions director was considering someone with an ACT of 35, then she can be about 99% certain that this interval, 3.39 to 3.83, would contain the predicted first-year GPA in college. Now, guys, we obviously live in a multivariable world, and we know that I've actually studied this quite a bit. And in predicting, course success and first-year GPA, you get into a lot of academic data. You also get into situational and dispositional data, which turn out to be actually more predictive of first-year success, i.e., first-year GPA, than placement test scores, than high school GPA, than ACT. So dispositional data, things about how much do you care, how motivated are you, how badly do you want to succeed. Situational data, how many jobs do you have kids. Those kinds of things are far more predictive. And we're going to get into that once we get into multiple regression. But right now we're setting the foundation for bigger and better stuff. All right, guys, one more thing before we end up this lecture. From time to time, we encounter situations where we have a known model. And I put known in parentheses or in quotes here because I'm not really sure that we ever know anything in statistics because all of our decisions are based on probability. But anyway, let's say that admissions director has been studying admissions data for years and years and years and years and years and seems to be pretty comfortable with his or her results. So we end up with a situation where our parameters are known. So there's no reason to So there's no reason to find the estimates because the assumption here is that they're known. So things change a little bit, not much. The overarching goal and the tricks, if you will, are the same. So let's just get quickly to an example. So let's say that admissions director has evidence that makes him or her believe that they can reasonably predict college GPA from high school GPA using the following model. And let's also furthermore assume that, remember, regression models are a function of three parameters: beta 0, beta 1, and sigma. Well, typically the variance, but we'll put it in terms of standard deviation. So guys, we can say that therefore the expected value of y can be found by taking and actually technically, guys, that should be a positive y. Still haven't figured out how to reset that. So I don't know. Let's just, again, hold x constant, and let's say that we're interested in a high school GPA of 3.80. So therefore, our expected value of y sub h for this level is 3.52. Now, let's say, for example, that we want to estimate the college GPA within plus or minus 2 standard deviations, which essentially gives us about 95% of our sampling distribution. So guys, what we would do here is we take our point estimate plus or minus 2 times our standard deviation. Let me just go back and check that. Yeah. So we're going to have 3.32 to 3.72. I wish it stayed that easy. Probably don't. It probably bore you to tears. So once we if we know S, I'm sorry, when this is known, there's no estimation of the sampling of the standard error of the sampling distribution. So we have easier problems. So guys, I'm going to wrap it up. I'm not going to waste any more of your time with trivial stuff. So this is the end of video 24. We're rolling on. Guys, next we're going to get into some what I think cooler stuff. It's not hard at all. We've seen it in a different kind of form, if you will. Just a ANOVA for comparing the means across K groups where K is 3 or bigger. But what we're going to do is we're going to look at the ANOVA for regression, and at the end of the day, this is just examining how we partition out the sum of squares and how the variance is partitioned out. And again, not hard, simple stuff, simple models, simple concepts, but what it ultimately is doing is setting the foundation for multiple regressions. So, guys, that'll be video number 25. So this is the end of video number 24. Have a good one.